everyone. In today's session, we are going to discuss about the principal component analysis, and it is a unsupervised machine learning algorithm which is generally used for the extraction of the feature from your datasets, and it is also used for the reduction of the dimension of your datasets. And generally, the principal component analysis is a dimension reduction and machine learning method which is used to simplify a large dataset into a smaller set while still maintaining a significant pattern and trends. And in today's session, we are going to use this PCA principal component analysis algorithms to reduce the features, the dimension of the features from these iris datasets. And once the feature are extracted using this PCA, then the extracted feature will be used for the visualization purpose using the MATLAB library. And generally, principal component analysis, or also can be said as PCA, is a dimension reduction algorithm that is often used to reduce the dimension of a large datasets by transforming a large set of variables into a smaller one that still contains most of the information in the large set. And generally, reducing the number of the variables of a dataset naturally comes at the expense of accuracy, but the tricks in dimensionality reduction is to trade a little accuracy for simplicity, because smaller datasets are easier to explore and visualize, and thus make analyzing the data points much easier and faster for machine learning algorithm without extraneous variable to process. So to sum up, the idea of PCA is simple. It is generally used for the reduction of the number of the variables of a dataset, while still preserving as much information as possible. And generally, the application of the principal component analysis can be seen here. It is used for the image compression, data visualization, noise filtering, feature extraction, and data processing. Generally, for the image compression, PCA reduces image dimension while retaining essential information. It helps to create the compact representation of the images, making them easier to store and transmit. Similarly, it can be also used for the data visualization. PCA helps to visualize the high dimension data by projecting it into a lower dimension space, such as a 2D or 3D plot. This simplifies data interpretation and exploration. Similarly, it can also be used for the noise filtering. PCA can remove noise or redundant information from the data by focusing on only the principal components that capture the underlying pattern. Similarly, it can also be used for the feature extraction purpose, and PCA can also be used to derive new features or elements from the original data that might be more insightful or understandable than the original feature. This is particularly helpful when the initial features are correlated or noisy. Similarly, it can be used for the data preprocessing, like PC can be used as a preprocessing step for other machine learning algorithms such as clustering and classification. What is principal component analysis? Generally, what is principal component? The principal component are a straight line that captures most of the variance of the data. They have direction and magnitude. Principal components are generally the orthogonal projection. They are the perpendicular projection of data onto a lower dimensional space. And this variance means it is a measure of how spread out the data is in a data set. If values are very similar, then it means the variance is low. If the values in a data set are widely spread, they have different values, then the variance is said to be extremely high. In machine learning or data analysis, high variance often means more information or patterns, differences, or signals in the data. So what generally the PCA does, PCA finds the direction, that is the new axis in the data along which the data varies the most. This that variance is not redundant or correlated with the previous axis. These directions are called principal components. Example PC1, PC2, and so on. PC1, first principal component, that is PC1, it is the direction with the highest variance, and similarly the second principal component, that is PC2, represents the represent the direction with the next highest variance after the PC1, orthogonal to the first principal component, and so on. There can be more two principal component. Next, this plot here, this plot shows the plot of the visualization of the principal component. Here the original orange dot represent the original 2D data, and here red arrows represent the principal components found by the PCA. The longer arrow PC1 shows the direction of maximum variance in the data, whereas the shorter arrow is orthogonal and capture the next most various data in a data sets. And why we are only considering the PC1 and PC2? The first few principal components generally capture the most of the important variation, that is information in the data set. For example, PC1 might contain 70% of the variance, and PC2 might contain only the 20% of the variance, and the rest might explain only small bit of variances. So therefore we select only the PC1 and PC2 components. For visualization, it is also used for the visualization. We often reduce the data to two dimensions, so we can plot it in 2D, like the scatter plot you just have seen in this figure. You can't easily visualize more than 2 or 3 dimensions. That's why PC1 and PC2 are the most commonly used principal component. Similarly, you use the PC1 and PC2 because you can use more PCs also beside PC1 and PC2. If you are not visualizing and just using the PCA for the like compression, noise removal, input to machine learning models, then you can choose any number of the components, even keep all of them, just rotate it into a new space, or just enough to retain 90% 5% of the variance. For example, here components are the PC1, PC2, PC3, PC4, and PC1 explained that there are 70% of the variance in the data sets, and PC2 represents 25% of the variance, whereas this PC3 and PC4 represents only the 3% and 2% of the variance. So we can neglect this PC3 and PC4 principal component, and we can only keep the PC1 and PC2 principal component, because they contain the most of the variance information. So it will be better to choose only the two principal components. In here, in these slides represent the steps for the PCA algorithms. First is the standardize the data. It means the PCA requires standardized data. So the first step is to standardize the data to ensure that all the variables have a mean of 0 and a standard deviation of 1. And in the second step, calculation of the covariance matrix is there. The next step is to calculate the covariance matrix of the standardized data. This matrix shows how each variable is related to every other variable in the dataset. And the next step is calculate the eigenvector and eigenvalues. And here the eigenvector and eigenvalues of the covariance matrix are calculated. The eigenvector represents the direction in which the data varies the most, while eigenvalue represents the amount of the variation along each eigenvector. Next is the choosing the principal component. The principal component are the eigenvectors with highest eigenvalues. This component represents the direction in which The data varies the most and are used to transform the original data into lower dimension space. And the next step is to transform the data. The final step is to transform the original data into the lower dimension space defined by the principal components. Now let's move to the coding part. And here in coding part we are not going to create this PCA from the scratch, but we are going to import this PCA that is present in the sklearn library. So this is the code how to implement PCA for the feature extraction. This line represents that I am importing the libraries for my, uses of the PCA. Here I have imported the NumPy, I have imported this matplotlib library for the visualization. Similarly, I am importing this PCA algorithms from the sklearn decomposition. And similarly, I am also importing the dataset, that is the iris dataset, and it contains the three different category of the flower is there. And I am importing these datasets from this sklearn.datasets. Next, to standardize the dataset, I am using the standard scalar function that is present in the sklearn.preprocessing. Now I'll run this code. This code is executed. Now next step is to load the iris datasets that I have imported from these sklearn.datasets. I will run this code, and here the X represents the features, that is the datasets. Generally this iris dataset contains only the features of the three different category of flower, but it does not contain the exact flower, only the features of the three different category of the flowers. So I have loaded my this iris dataset in this iris, and from this iris I am extracting the features, that is the X datasets. And similarly I am also extracting this Y datasets Y, and generally this Y is the label of my images, features of the images X. I will run this. Now I will show you here this X. Generally I think this X contains near about 150 images. X dot shape. Yeah, it contains 150 images, 150 features of the three different category of the flower images, and it has four dimensions. Generally four features are there: first feature, second feature, third feature, and fourth feature are there, of total 150 samples. I will show you these features here. This, if I print this, it will display 150 features. These are the 150 features. This represent the first represent the first dimension. This represent the second feature, second dimension. This represent the third feature, third dimension, and this represent the fourth feature, fourth dimension. Altogether there are 150 samples, and four features are there, four dimension are there. So now next part. Now next step is to standardize this data, which is generally very important for the application of the principal component analysis algorithm. So I have already imported this standard scalar from the sklearn.processing. I am using this standard scalar function here, and then after that I am standardizing my dataset X, that is the features, and it contains the 150 samples with four dimension. And I will run this code. Now this code is on. Now I will show you here. This, I think this X scale still contains the 150 samples, and four dimensions should be there. It's saved. Yeah, it still contains the 150 images and the four dimension, in four dimension 150 features, and there are altogether four dimension are there of the 150 features of different three category of flower images. Now next step is to apply the PCA algorithms, and I have already imported this PCA algorithm from this sklearn library. I am just using this PCA now here. PCA, and I have specified that number of the components, that is the principal component, should be only two. I want only two component, not all four component. So I have specified that parameter here too, and I am saving this in the new model name, that is PCA. And then after that I am passing my standardized data set to these PCA algorithms. Now I will run this code. Yeah, this code has been executed. I'll show you this XPCA. Its shape, I think its shape should be reduced to 2 dimension, because I have specified the number of the principal component as 2. Here you can see here, previously my data set has 4 dimension, and now after applying these PCA algorithms, my dimension has been reduced to 2. It means we use this PCA for the reduction of the dimension, because in order to process the larger data set, higher dimension data sets, it is extremely harder, because the training time generally takes long, and noise can also be there. So to filter my data sets, to reduce the size of my data sets, I am using here PCA for the reduction of the dimension of the data sets. Now this code also similarly for the same task, it prints the shape of my data set. Previously it was in 4 dimension, and after applying PCA the dimension has been reduced to 2. And in both these samples, X and XPCA, there are 150 features of the 3 different category of the flower. Now this code is used to see the 5 features, 5 features from the beginning. These are the 5 features. You can see here, previously there were 5 dimension over there. Here X. If you see here, if you execute this code, you can see here 5 features are there. 4 features are there: first dimension, second dimension, third dimension, fourth dimension. But after applying this PCA, its dimension has been reduced. Only the 2 dimension are left because of this PCA. Now in this line of the code, I'm trying to visualize my features that has been extracted from this PCA. This represents the first principal component, this one, and this one represents the second principal component, second features, this one. I am using the color map bodies here, and here C equal to Y argument colors the point by their target class, specifies that is specified in the iris dataset, and this is the age color should be K. It means the color of the points should be in black color, and this represents the size of these points. Now I will run this code. Now you can see here, these are the features that has been extracted from the PCA. Here geo is the first category of the flower, this one represents the second category of the flower, and this two represents the third category of the flower. Altogether there are 3 categories of the flower. This is the first category, this is the second category, and this yellow represents the third category of the flower. Here K represents the boundary of this point. The edge of this circle should be in black color, and whereas this S control the size of the that circle, that point, if I make it 8.